Okay, let's have a look at example 59. I'm not going to go through the details, but we want to see the big picture here so that we can apply it in more situations. So here we have a bag, A, has a mass of 3 kilograms, released from rest at this position, and they say theta equals 0 degrees. After falling to 90 degrees, it strikes an 9 kilogram box. That's not right. It strikes a 9 kilogram box. Okay, B, if the coefficient of restitution between the bag and box is E equals 0.5, determine the velocities. Okay, this is what I've been saying in the previous videos. Determine the velocities of the bag and box after impact. Okay, so there's question 1, the velocities after impact. And what is the loss of energy during the collision? Okay, so there are 2 questions. And how are we going to solve this? Well, the first thing we need to see, remember earlier on we spoke about central impact and oblique impact. Now I'm going to touch on oblique impact after I've done a few central impact problems. Then we will look at oblique impact and we'll do some oblique impact problems. Okay? But the first thing we need to see is that this is a central impact problem. Why is that? Because the direction of motion of the mass centers, okay, are along the line of impact. Okay, remember, what is the line of impact? If you've got 2 particles colliding, right, we have the plane, this plane over here, and if you draw a perpendicular line to that plane, then that is the line of impact. So even if you've, but these 2 particles can either be traveling along along that line of action toward each other, or they can be traveling at an angle. So if this particle is traveling in that direction, this particle is traveling in that direction, there's the line of action, which is perpendicular to this collision plane, this plane of impact. So there's the line of action. If they're traveling at an angle, then it's oblique. But if they're traveling along those 2 lines toward each other, then it'll be central impact. So this is central impact because when the bag, if there's the bag, it hits, it is traveling along this line of impact, and the box will end up also traveling along that line of impact. Okay? So that is why it's central impact. Make sure you know what the difference is, but it's pretty obvious, I think. Okay, so central impact, those are the 2 questions. So what do we need to do? So we want, remember that what are the velocities after impact? Well, we know. I can just use my coefficient of restitution, VB2 minus VA2 over VA1 minus VB1. Okay? So if I've got my initial velocities before impact, and I've got this is 0.5, I have a chance of calculating my velocities after impact. So what do I need? Well, I need the velocities before impact. So that's B and that's A. So what is the velocity of B? Well, it's stationary. We know VB1 is 0. So that's 0. VA1, how am I going to calculate VA1? I just use the conservation of energy. It falls from this height, and I'm able to then use the conservation of energy to calculate my VA1. I'm able to calculate this value there. Okay, I'm not going to go through that. You can figure that out. Okay, so we've got this, that's equal to 0. That's equal to 0. We've got this equal to 0.5, but we don't have VB2 and VA2. Okay, so what else do we need then? Well, because it's a collision problem, it's an impact problem, we know that this now forms our system. These are internal impulses occurring, so it's closed and isolated system. So we can use the conservation of momentum. No external impulses. The initial momentum, the sum of the momentum at the beginning for the particles equals the sum of momentum at after impact. Okay? So we know that VB1 was 0, and we calculated VA1. So we got VA1 here to be 4.429 equals mass times velocity plus mass times velocity, and we're going to have two unknowns here, VB2 and VA2 in this equation, and there we have our final equation from conservation of momentum. So then we do exactly what I did here. We look at the coefficient of restitution, and as you can see, I explained this. Our two unknowns were VB2 and VA2. So here again we've got two unknowns. So two unknowns, VA2, VB2, and two unknowns, VA2, VB2, and you could solve them simultaneously using simultaneous equations. You calculate VA2 as minus 0.554. Now, what's important to notice here is left was taken as positive in both of these problems. Okay? So, if we got a negative, then it means that VA2 was after collision. What happened to VA? What happened to A? After collision, it moved to the right. After collision, does it make sense? It hit the box, and then it rebounded, and it would rebound, right? Because E is equal to 0.5. When will it not rebound? What can you answer that? When will there be no rebounding? Only when E is 0, right? Then our restitution impulse is 0. Okay? But if it's 0.5, then it has to rebound somewhat, and in this case it rebounds and it moves to the right. Then what happens to particle B? It moves to it started at 0 meters per second, and then there was this transfer of energy, even though there was energy lost, and we had B moving to the left at 1.66. Okay, so there we've solved question 1, solved. Now, the second thing is, what is the loss of energy? Okay, and remember, if E is less than 1, then we've lost some energy to thermal energy, to sound, stuff like that. Okay, now how do you calculate it? Well, we can use this. T1 plus the sum of the work from 1 to 2 is T2, and then if you rearrange it, you can see that the energy lost here is simply the final kinetic energy minus the initial kinetic energy. And for this, we needed these velocities. Okay, so again, I'm not going to go into the detail. You just carry it out. You just look. It's right here. It's the final kinetic energy minus the initial kinetic energy. And as you can see, we've lost, during the collision, we've lost 16.6 joules of energy during the collision. Okay? And the energy loss occurs due to inelastic deformation during the collision. Okay? Alright, I hope you guys are getting the idea. See you in the next problem.